pumping lemma under module 1 of automata theory and computability. So let me see the presentation flow as follows. At the beginning we will going to discuss the regular expression and non-regular language, regular and non-regular language. So followed by the pumping lemma, the concepts will be going to be discussed in the proving of that, and also so that how to apply to test the given language is regular or not. So before knowing this, know the what is regular language. Regular language and automata seem to be more powerful. After all, they employ to model everything in the literature. But there are many simple examples that are not regular languages, but it looks like a regular. But when you are subjected to the pumping lemma, we will able to know that that is not a regular language. Before going to understand the pumping lemma concept, we will discuss more about what are the differences between the regular language and non-regular languages. Right? So regular language, it follows certain patterns or uniform patterns, maybe 2, 4, 6, 8. There exists a pattern that such a language follow, whether you see it or not. On the other hand, non-regular language do not follow any pattern. For example, set of prime numbers, right? Some non-uniform distribution over the pattern. Such examples are the best example for the non-regular languages. The regular language can be modeled by finite automata, but non-regular language, it is quite difficult to model. Sometimes it cannot. All of whose members can be expressed with help of regular expression. So the proper term for this string maybe can express through the regular expression. In the non-regular languages are those whose members cannot be expressed with a regular expression. Right? So members cannot be expressed with a regular expression as a regular language does for the strings which involved in that language. From above this point, regular language concepts we are able to disseminate or understand. It is clear from this point. Further, non-regular language can be tested through the certain hypothesis. One such hypothesis called pumping lemma test. If you make an undergoes these non-regular languages for that, you can certify that these are the non-regular language because this pumping lemma test has become failed. In that case, we can directly decree it. It may not show as per regular language, right? We cannot exercise the pumping lemma for non-regular languages, right? So the one best example for regular language, that is A star, B star. A star indicates the clean star, right? So that may be 0, 1, 2, so on, that is. Whereas the non-regular language, that is a example A power n and B power n, right? N is greater than 0. The pumping lemma further strategy for proving the languages to be non-regular that have all special properties. So this special property, language cannot be a regular. So the property that states that all strings in a regular language can be pumped if they are at least as long as the special value, the pumping length, right? This means that each such strings contains a section that can be repeated any number of times, with the resulting string remain in the language, right? So further, pumping lemma expressed through with the inherent conditions. They lay down some conditions. Those conditions are 3 conditions. Let L be the regular language and number of B the pumping length, where S is a string, That language S may be broken into three parts. S is equal to UVW satisfying the following conditions. First condition is V is not equal to empty, but U and W may be empty. The middle one, when the S string is divided into three components called UVW, the first condition is V never be empty. It may not true in the case of U and W. The together length, that is the length of UV, should be less than or equal to P, right? The maximum P value is UV. It does not go beyond that UV length. For each K is equal to greater than or equal to 0, U V power K W, that belongs to L. So these three conditions are extensively exercised over the given language to prove that the given language is not regular, right? The first condition, V should not be equal to 0, empty, the UV length should be as equal to P or less than. For each K, that is K is greater than 0, K is equal to 0 to N, that is U power V, U V power K W belongs to L. This theorem says further, S is a split into UVW, either U or W may be empty, but V may not be so. U and V together must have length at most P, right? So always find a non-empty string V not too far from the beginning of S that can be pumped, that can be repeated any number of times, right? So note that V is not equal to empty. For the third condition, K is equal to 0 to N, that is V power 0 is equal to empty. Then UVW must be belongs to L. If it is not belongs to L, then it is not satisfy the pumping lemma postulates. So testing is failure. So in that case, can directly declare that that language, the testing language is not regular. Further, in the proof way, consider the simple case of regular language L. In this L, there is no string of length at least P. In this case, what will happen? Theorem become unintelligently true, right? It is a very rude way to decide. The three conditions holds for all strings of length at least P if there are not any such strings, right? If L is a composed of simply the finite set of A, then we could pick P is equal to 2. The theorem is vacuously true, that is unintelligently true, rudely true, because there are no strings of length at least 2. This implies for any finite set of string, the L is R, since we pick a value P is greater than the biggest strings of the string in a L, right? So further, more general case, suppose that L is a regular, in that case that language L is equal to L of A for some DFA A, some DFA deterministic finite automata A. Suppose that A has n states, A has n states. So consider any string S of length n or more, and say that A will be split into three components, that is UVW. Before splitting, we can see what is a S. A is contains A1, A2, A3, so on AM, where M is a greater than N or equal to N, right? String S we have taken as a entire gamut. So S is equal to A1, A2 till AM, right? So this is a considered string of the language L. So for I is equal to 0 to N to M, define the step Pi, state Pi to be delta cap of Q0 comma A1, A2, AI. The strings A1 to AM will be splitted into, after splitting, the first component is called U, so that is nothing but A1, A2, AI, right? A1, A2, AI. That is, Pi is the state that A is after reading the first I symbol of S, right? First I symbol of S till ith symbol, right? The first ith symbol that is a part of the S is going to be that as per the planar pumping lemma, that S will going to be broken into three components, that is UVW. The first U is accommodated with the A1, A2 till AI, right? The first ith number of symbols of S will be taken out. So by the pigeonhole principle, since there are more input symbols, what are those inputs? That is, S is equal to A1, A2 to AM. These are the more inputs symbols are there. So these symbols will be broken into three component UVW as per the conditions of the pumping lemma, right? So after splitting, that is, we will get the uniform number of characters or non-uniform length of the characters will be getting for UVW. That again decided by the pumping lemma, right? So Vi not equal, V over I is not equal to 0, but U and W may be 0, but each length may be varies, right? So by the pigeonhole principle, since there are more number of input symbols are there, then there are the states, we must repeat some state more than the ones, right? More than the ones. So what will happen here? The number of inputs are more and the number of states are less. If so, what will happen? The sum of the inputs we have to put more number of inputs we have to put in a particular state. Even if we put uniformly the less number of inputs to each state, some states will be remain idle because they are not possible to accommodate any states. So that's why certain states will get more number of inputs. In that case, pigeonhole principle might help us here. So here we can say that we must repeat the sum of the state more than the ones. If so, sum of the states more than the ones. Thus we can find two different integers I and j with the 0 to j, 0 to n is there, that will be split into partition, that 0 to I to j, j to n, such that Pi is equal to Pj. Break S into S is equal to UVW as follows. So U is equal to A1, A2, AI, A1, A2, A3, A4, so on AI. V is equal to AI plus 1, AI plus 2, and AI. So W is equal to AI plus 1, AJ plus 1, AJ plus 2, AM, right? So U is equal to A1 to AI, V is equal to AI plus 1 to AJ, W is equal to AJ plus 1 to M. I hope it is clear, right? So given S will be partitioned into UVW. So U is A1 to AI, V is equal to AI plus 1 to AJ. So AJ, W is equal to AJ plus 1 to AM, right? So complete partition happens. So the string U takes the state Pi, U, then somehow they repeat back to that state at this point, input symbol J and the corresponding state Pj, where Pi is equal to Pj. Finally end by moving in accepting state, right? Finally end by moving in by accepting state. So here, since I is less than j, not less than or equal to j, this means that it must have at least one symbol for V, right? V should not be empty. So V may not be empty. In general, V power I W belongs to L. The L is we assumed at the beginning is a regular. Now we want to prove the same according to pumping lemma. We'll see what will happen. So if I is equal to 0 to 1 to n, and you can see that the U part, that is A1, A2, A3, till AI, right? So that is a U. S is broken into three component called UVW. First is a U. So U will be going to be accommodated A1, A2, AI, right? So that is a U, right? So A1, A2, AI, A3, A4, AI till this point A1 to AI, U. So next we have V. So V power I, right? V power I. So that is I is equal to I plus 1, AI plus 1, AI plus 2, AI plus 3 till AJ, right? That will be in the loop. So that will be concept of Bhajantri principle help us to put the more number of inputs in a states, right? More number of inputs in a single state called Q, right? So next we can have this is a VI. So next we can have W, right? W is what? AJ plus 1, AJ plus 2, AJ plus 3, so on up to AN, right? So by this time it will reach the parallel state with the indication of the double circle. So I say that is an accepting state. We can have further animation or with a more information. So we have P0 to Pi, that is U0 to U0, U equal to A1 to AI, and Pi, that is AI plus 1 to AJ, that is B, and AJ plus 1 to AM, that is W. So ultimately reach the final state. So this have provided the enough information about the skeleton of the pumping lemma. This pumping lemma we can exercise to test the given language is regular or not. At the beginning, assume L is a regular in order to observe the contradiction, right? So if any contradiction arises during proving that the given language is a regular, so then that contradiction is itself evidences to declare that the assumed language is a not regular. Then use the pumping lemma, guarantee that existence of the pumping length P such that all strings of length at least P can be pumped. P number of characters we need to be pumped, right? P number of characters. So that is the length of the UV. Find the string S in a language L that has a length P or greater than but cannot be pumped. Greater cannot be pumped. So this demonstrated by the considering all ways of dividing S into UV and W and tells one or more of the conditions of the pumping lemma are violated or not, right? You can just poke our nose to whether conditions are going to be violate or disturbed, right? So typically that three conditions, third condition is most of the time is going to be violating, right? So since the existence of the S contradicts the pumping lemma, if L was a or regular, means that L is a not regular now, right? So pumping lemma, the further tricky part, coming up with the strings. This may take some additional thinking, and also trial and error approaches also sometimes works, because for non-regular language some strings may fit the pumping lemma conditions while others will not, right? So that's why some trial and error method or some extra thinking may be essential to exercise over to test the given language is regular or not through the pumping lemma postulate, right? If string works, you may need to pick another one until you find that leads to the contradiction. Maybe one string may not enough, so you can take the multiple strings, so and put an extra effort to reveal whether any contradiction or exist here, right? So exhaustively you have to dig out whether any contradictions are maybe looks like a nuggets which are we need to be mine them. Right? So pumping lemma as a glance. So think of pumping lemma maybe an adversal game, right? Through the game we can decide the how this pumping lemma plays. Just consider player 1 and player 2 involved in this game. So assume that the player 1 picks the language L to be proved non-regular. He took the language and immediately proved that is by player 1. So player 2 what will do? He will put some extra effort. Pick P, the pumping length, and P1 does not know what P is. So P1 must devise a game plan that works for all possible P's. We must leave P as a variable. The difference between the player 1 and player 2, player 1 just proved the given language is non-regular, but player 2 exercise some extra effort by having a length of P, that is a P, that is a pumping length he called, then he also proved, right? Both are proved, but player 2 flow more evidences, right? So the next player 1 becomes smart and is also ready to put extra effort, picks a string S and where S is in L, right? He may be going to be in the same way that P2 doing during second attempt. So now P2 obviously he is known for the putting some extra effort, no? As a first case study we have seen. So P2 divides S into UVW, obeying the construction that are stipulated in the pumping length. V is not equal to empty, UV should be less than P, and UV star W belongs to L, right? So P2 is smart compared to the P1. So of course P2 won that case, right? P2 has produced the more evidences. So now P1 is want to become further smart than P2, right? P1 wins by picking K, right? So V power star W it belongs to L, that was by the P2 tricks. Now P1 has improved over that by putting a star instead of star he putting the I, that is a UV power I W, that is a UV power K, picking K, which may be the function of P, right? UV or W such that UV power K W is not in regular language, right? So P1 does that is. So this game assumes that P2 is a smart and if possible to pick any UVW, that is S, that does obey the constraints of pumping lemma postulates, then he will do so that, right? So I hope you will be observed from this game between player 1 and player 2. Every time they are competitive in nature. So they are exercising that pumping lemma indirectly, but the part they are going to be employing, right? So at the end P2 shows more smartness, is aggressive than the P1, right? So we can have some of the examples we are going to be try after understanding the concept of the pumping lemma, right? So now we can see the example A power n and B power n, where n is greater than or equal to 1. Prove is not a regular language, right? So just glance the problem, A power n and B power n, where n is greater than or equal to 0, right? 1. Prove is it not a regular language, right? So we can, as we see that previous concept of the pumping lemma, split the given string S from this language L, consider the string S from this language L and divide them into U, V power K and W, right? So where we have, since UV is the less than or equal to P, both U and V must have S only, and we can see that S will be split into U V power K W. L is equal to what? A power U is equal to A power n minus 1, right? A power n minus 1. So V is equal to A, that is A1. B, that is W is equal to B power n. A power n and B power n is split among UVW. U is equal to A power n minus 1 and 1 A is remaining, that will put it into the place of V. That's all, right? So W will be undisturbed, that is completely B will be placed in the W place, that is B power n. So A power n we have taken, that is put it among U and V, that is A power n minus 1 and A power 1. So altogether it is A power n, For example, n is equal to 4 you can put. If n is equal to 4, then 4 a's will be there. Out of 4a, 3 will be put into the u and 1 a for the v. And 4b, n is equal to 4. 4b is exclusively for w. Right? So if since uv less than b, both u and b must have a only. If pump down the k is equal to 0, then string v power 0, that will be vanished. Right? So in that case, a b b, for example, k is equal to 2, n is equal to 2. If n is equal to 2, a b b. So if n is equal to 3, a b b, right? If n is equal to 4, that is 3 a's and 4 b's, so on that is. So n is equal to 4 we have demonstrated here, right? So let me proceed how this string will be broken down into. So s naught. So s naught, that is k is equal to 0. So k is equal to 0 here we have. So u power v 0, u power v power 0 w is equal to a power u is equal to what? A power n minus 1. What is a u0? u0 is a epsilon, that is empty. What is a w? B power n. So altogether what will happen? A power n minus 1 b power n. So it not belongs to L, because a power n followed by b power n. Number of a's would be equal to number of b's, but here one less a is there. So a less a is there. So it not belongs to L. Right? So similarly we can have s1 u power uv power 1 w, that is a v power I, k is equal to 1, k is equal to 1, that is a power n minus 1, a power n minus 1, a power 1, b power n. What is a power n minus 1? That is a u. What is a power 1? That is b power 1. What is a b power n? That is w. Right? So altogether a we can merge them. So a power n will be there. Right? So a power n and b power n will be emerging. So a power n and b power n are almost the language. In other words, it is a proof that it belongs to language here. So nice, right? So we can go for s equal to 2, that is k is equal to 2. So uv power 2 w, right? So a is equal to a power n minus 1, a power 1, a power n, b power n. What is a u is equal to a power n minus 1. What is a v square is? That is a square. A square you can put, right, a power 1 and a power n, b power 1, that is w, right? So you can merge all these a's. So then we will ultimately emerge with a power n plus 1. So the final b power n will keep as it is. So a power n plus 1 and b power 1 is not belongs to language L, because more number of a's and less number of b's. Less not n number of a's or b's are there. So extra a's will be there. Hence it is not belonging to language. So overall summary, you can k is equal to 0 and k is equal to 2. The string sk will not have equal number of a's, either less or more. Right? When k is equal to 1, so that have equal number of a's. So the k is equal to 1 and k is equal to 0 and 2 leads the contradiction. The number of a's are not equal and it leads the contradiction. This contradiction is enough to prove that the given language is not regular, right? So I hope it is clear from this example. So let me proceed for the second example. So a power n. So the n is a perfect square. Prove is not regular language. So solution: so split the perfect square into u v power k and w, right? So since uv is less than equal to p, uv is less than equal to p, both u and v and w must have a's only, because in the problem a's are there, a's only there, right? So you can split now uv w, that is a power n. So let consider L is equal to that is a L language, the string s u v power k. So u is equal to a power n minus 2, u is equal to a power n minus 1. What is a v? V is a power 1, right? What is a v? V is a power n. And what is a w? A power 1, right? So altogether a power 1 and a power 1, a power 2. So a power n minus 2 is there. So combining all this, a power 0. So nothing will be taken, that is. So to just prove we have taken, that is n is equal to 4, we can apply. So that is a 2 a's will be there, u will be 1a, w will be 1a, right? So we can proceed further. If we pump down k is equal to 0, then string will be, what will happen, k is equal to 0 is a 2a, 3a, 4a, 5a, so on, that is right. So let's go to the important part of the this testing phase, that is a perfect square 0 u v power 0 w is equal to a power n minus 1 epsilon p power n, right? What is a u? U is equal to a power n minus 2, right? So that is wrong, I put that a power n minus 1, so this is a power n minus 2, right? So no, this is totally wrong. So leave about this perfect square case 0. So we'll go to the perfect square 1, right? So perfect square 1, this is wrong, so I should not taken that b, right? So from the perfect square 1 now onwards, it going to be correct, right? So u power v power 1 w, u v power 1 w, that k is equal to 1 is equal to a power n minus 2. What is that? U is equal to a power n minus 2. A power 1 is what? V. A power 1 is what? V power 1. So a power 1, last a power 1 is w, right? V power 1 is equal to a power 1, w is equal to a power 1, or v power 1 is equal to a and w is equal to a, right? So these two will be merged here and will be remain a power n, right? Remain a power n, so belongs to n, right? So a power n is a perfect square, right? So that a power n we need to be maintained in the that system, right? Next, k is equal to 2, uv power 2, that is w, is equal to a power n minus 2, a power 1, a power 1, a power 1 is equal to a power n minus plus 1, sorry, a power n plus 1. So what is a u? A power n minus 2. What is a v square? That is a power 1 and a power 1 or a power 2. What is w? A power 1. So combine all these. How many a's are there? 3 a's are there. Extra 2 is here. So 1 will be there. A plus a power n plus 1. So it not belongs to m. So we need only a power n. It happened in the second case, but earlier also it not happen. But I take one wrong. That is, but it will not happen. It will not happen here. So these two are end up with contradictions. So n number of a's are there, but extra 1 a will be coming. So we can declare that due to this evidence will the witness for contradiction. So k is equal to 1 and k is equal to 1, that is a ps, that is k is equal to 0 will be showing that is a string psk will not have perfect square for any value, right? So hence it is not regular language, right? So example 3, we can have language is equal to z power r. So which that is nothing but z is belongs to, that is strings or input symbols a comma b. Fru is not a regular language. So consider z is a string and z power r is a reverse of that, right? So solution split the word into z power r into u v power k, v power k and w. Since u v less than p, both u and v and w must have a's only. That if you taken a a's, that is u is equal to a minus 1, a power minus 1, v power k is equal to a, w is equal to epsilon, right? That is a null. So altogether what will happen? It is a null. So null thing will be added into here, right? So if you k is equal to 0, that is down, the number of characters should be down, pumping down the strings. Example A will be generated. So let's consider the different cases here. Two cases are going to be considered. One case for A and second case for the B, because the input symbols are A and B, right? So the first case is A will be taken. The next case will be taken B. So the case one U is equal to A, right? So what will happen? U is equal to A. So here the U is equal to ZZ power R A minus 1, comma V is equal to A and W is equal to epsilon, right? So initially we need to be consider string S into VW. U is equal to ZZ power R A minus 1, V is equal to A, W is equal to epsilon, right? Three compartment, right? So let me continue. So Z0, that is a UV power 0 W is equal to UV power 0 W is equal to ZZR, that is A minus 1, this complete U. What is a V power 0? Is epsilon. What is a W? Is epsilon, right? So ZZ power R A minus 1. This will be complete string will be merged and put it in a consolidated way. ZZ power R and A minus 1 is not belongs to L, because one A will be less. So though A we have forcibly putted here A, but while we want to prove that it should that forcibly putted B should be vanished, it should not be represent the final results. Continue. Z, that is a Z1, that is equal to K is equal to 1, U V power 1 W is equal to ZZ power R A minus 1 A1 epsilon. What is that U? U is nothing but ZZ power R A minus 1. What is a V power 1? That is A power 1. What is a W? Is a epsilon, right? We can merge all this now. So ZZ power R belongs to L. The minus 1 plus 1 will be vanish together, and we have ZZ power R belongs to L. Compared to the previous one, there is ZZ power R A minus 1 was there. So now we have ZZ power R is A will be vanishes here. So it says the belongingness, it declares the belongingness. Of course there is a contradiction between these two. Now it is not a right time to decide. Let me further can go one more example, that K is equal to 2. So Z2, that is Z2 is equal to UV power 2. So W, so is equal to ZZ power R A minus 1 A plus 1 A plus 1 W C epsilon. So ZZ power R A minus 1 is complete U, and A1 is complete V square. The last epsilon, that is a W, right? So ZZ power R A is a outcome. So extra A's will be there. Since this extra A may leads to contradiction, so it declared that it is not belongs to language, right? So let's go for the case 2 of the same problem. So there we have taken A, now we will take a B, right? B. U is equal to B minus 1, V is equal to B, and W is equal to epsilon. So U is equal to ZZ power R, so A minus 1, so this is a B minus 1, this is B, and V is equal to B, right? So W epsilon, and the first case one is okay, the second case one is B, and V is equal to B, W is equal to epsilon. So Z is equal to UV power 0 W. What is a U? ZZ power R B minus 1. What is a V0? V power 0, that is epsilon. What is a W? That is epsilon. So altogether what will happen? ZZ power R B minus 1 is remaining. So it never belongs to language L, because extra B minus B will be there. So that is a contradiction. So Z is equal to 1, so K is equal to 1, so UV power 1 W, that is equal to ZZ power R B minus 1 B epsilon. So ZZ power R is a not belongs to is belongs to L. Sorry, is belongs to L because no added characters are available here. So minus P plus P is together will be it leads the vanish that no letter will be witness for the final results. So ZZ power R is a result is emerging. So it belongs to L. So V K is equal to 2. So K is equal to 2, what will happen? UV power 2W. What is a U? ZZ power R B minus 1. What is a V square? So that is B square is a double B or B square. B you can put either way, B plus 1, B plus 1 or B square, right? So what is a W? Epsilon. So altogether one B will be anissus, ZZ power R and B is not belongs to L. So the result we got ZZ power R B. The result we got ZZ power R B. So is one extra B is coming here. Extra B is coming here, right? So hence it is not belongs to regular language. By observing this case 1 and case 2, so case 1, K is equal to 0 and 2 shows the not belongingness. K is equal to 1 shows belongingness, right? So when case 2, that is when we consider for the B, right? U is equal to B. So K is equal to 0 and 2 it shows the not belongingness. K is equal to 1 definitely shows the belongingness. So the different case are isolating. Different K are oscillating, right? So oscillating in the sense that it give an evidence to the contradiction, right? So this contradiction help us to prove the given language is not regular. From these 3 examples, so I hope you will be got some idea about how to test the given language is regular or not through the pumping lemma. So we add one more example, that is a 0 power I and 1 power j. 0 power I and 1 power j, where I is more than the j, that is a condition. So that non-regular language using pumping lemma. Assume E is P is to be a pumping length, choose S to be the string 0 power P plus 1 and 1 power P. Because I is greater than j, no? Put extra 1 for P. For O can put 1 extra. So here clearly a length at least P and it is also in the language, right? So split the S strings into UVW, right? So that what is a U? U is equal to 0 power V, 0 power P. What is a U? 0 U power P. What is a V? So 0 power 1, right? So 1 extra is there, no? 0 power V. What is a W? 1 power P. So UV will be completely 0, W will be 1, right? So since UV is less than the P, both U and V must consist entirely zeros. So if you pump the P up, K is greater than 0, then ended with the strings 001, 0011, right? Or still in regular language. If you push V down by allowing the K is equal to 0, then getting the strings UW, the 01, 0011, right? So removing that V decrease the number of zeros in S, but construct S so exactly one more 0 than 1, right? So by deleting the zeros, remain the same fewer zeros than ones. So the resulting string is no longer belongs to the language E. Language E, we assume initially it is a regular. From this contradiction, we can say it is not a regular language, right? So I hope you understand the concept of the non-regular and non-regular languages. After knowing the definitions and their the minor differences, from that we motivated to test the given language is a regular, not regular, right? So basically we went to think about whether the given language is not regular. So for which the pumping lemma extended enough help to prove that the given language is. So that necessarily creates the contradictions. So thus contradictions are enough evidences to say that a given language is not regular. From these 4 examples we gone under thoroughly, right? So thanks for watching video lecture on pumping lemma concept. If you have any queries, you post these queries to this mail ID. Thank you once again.